Everybody, thanks for showing up through the rain. Today's lecture is going to be a follow-up on last week's talk on anatomy, and then we're going to get into Da Vinci studies on friction and wear, and there's going to be a case study with respect to rail, rolling surfaces on rail. So as a follow-up from last week, we discussed that a lot of Da Vinci's work was based on geometrical principles, and he looked at the human body as a structurally assembled system. One of the issues that we discussed last week was to understand the size scales we're talking about. So Da Vinci had came up with his own measurement called the cubit, but if you're talking about biological systems, we showed last week that it can go down to nanometer size scale. So when we're talking about structural systems, it's important to understand what length scales we're talking about. The image here is the Vitruvian Man, and in this is we discussed the balance of the representative body with respect to geometry and perspective. We've tied that into radiography, X-rays, and current implications to the technology with respect to artificial intelligence, neural networks, the ethics and morals when you can get down to a size scale in someone's body for either ingestible electronics. There's quite a bit of research going on that route. If something is at such a small feature size that you can't remove it through the body naturally, there's ethical considerations to that. One thing I wanted to point out, this is actually from one of Da Vinci's notebooks. It's a replica of the notebook, but when we talked about the Vitruvian Man, we discussed these geometrical principles that he was talking about. And you can see his sketches. This is basically geometrical sketches related to that piece of artwork, where you see the various locations of where the body could have been placed. One of the other things I had mentioned in an earlier lecture was Da Vinci had a very unique way of writing. He actually wrote from right to left, which was counterintuitive for the time. So Da Vinci put in these subtle ways in his writing as a form of intellectual property 500 or so years ago. The other thing that I was found interesting is that they describe it as a form of mirroring. So if you looked at this writing in the mirror, it would look how it's supposed to look. So he naturally wrote things in a reflection of itself. So tying in today, before we get into friction and wear, I did want to show a couple more sketches of the anatomy. Da Vinci did, in addition to the work on the heart and on the veins and the cardiovascular system that we talked about, he also did sketches on the human body, the feet. If you remember last week, the Vitruvian Man, he had those two representations of the foot where he has the human body as represented as 4 cubits in length. If you looked at the foot in that artwork, he has it represented in multiple orientations. So he did quite a bit of work on the bone structure, but what I wanted to follow up with is related to the human skull and what we talked about in terms of blunt force trauma. And we talked about a technique called digital image correlation. So this is actually on Stellar. I posted these things on Stellar under the materials section if you're interested in it, but digital image correlation is a non-destructive technique. And if you think about it, it's very similar to your GPS where it triangulates the system. What they're doing with this is it triangulates based on 2 optical camera systems. So you have the 2 camera systems set up at a set distance, and based on that, they put a speckle pattern on what the area to be interrogated is, and due to the pixel size and the voxel size, that speckle pattern gives enough randomness to what they're looking at that if you're looking at, for a nuclear plant, for instance, if you put it under pressure, you can see the stress. You can see stress and strain. So it's a way to, they describe it as a way to get virtual stress and strain based on the optical features under inspection. This is actually a couple images from a project I worked on about 5-6 years ago. So what we're seeing here is this is the digital image correlation cameras here. You have these calibration blocks and they each have various targets on them. These targets, the reflectance, there's different levels of reflectance. So one of the issues with the digital image correlation, with it being optical technique, is if it's a very bright surface, you're going to drop some of those images due to the reflectance and the brightness. So they actually set this up as a calibration to know what the threshold for brightness or darkness is in the image. And that stays here. This is your random speckle pattern here, and this is actually a wall on the containment of an operating nuclear plant in the US. So what happened was that in order to prove to the NRC, Nuclear Regulatory Commission, that there was no degradation inside the containment that you couldn't access with a human, they allowed us to go in there and set up this speckle pattern, and we actually performed the digital image correlation while the nuclear plant did what's known as a structural integrity test. So they have to do this test to prove to the NRC that they don't have any degradation to the primary containment. So you don't want to have loss of primary containment and any type of loss of coolant as a resultant. But what you're seeing in the image here is from the speckle pattern here, this is what would be referred to as a cold joint. So as they're building that containment, you can only pour so much concrete every day while they're building the plant. So what happens is when you finish one pour and you go on to the next pour, you'd get what's known as cold joints along the vertical height in the containment. These other areas here are just other areas related to stresses due to the anisotropy of concrete. So this was at a 35 psi pressure. The entire containment basically goes under pressure. The image here you're seeing, it's basically what I already discussed. You have the speckle pattern, you have your two cameras, and then you have your calibration plate. Couple things to note in terms of sensitivity is that the system defines areas typically 5 to 20 square pixels in area. So when we talk about that, that's where that random speckle pattern comes into play. If the random speckles are larger than that 20 square pixels, as the wall is under pressure, that will actually move. And then the cameras can track those movements, and then they back calculate stress out of it. It tracks the facets from successive images. Its sensitivity is approximately 1/30,000th the field of view. So depending on how far they place these cameras from the wall affects the sensitivity. That's your field of view, how far back they're going to place these cameras. But it is a technique that's useful if you can't actually put a person there and get access.
How do you back evaluate the stresses? Because I've been doing DIC also for my research, and I'm finding problems in back evaluating the stresses since we don't have a simple tensile stress application usually, but it's biaxial. So how do you take that into account for materials that are not isotropic?
One of the ways we did it in this project was actually to take tensile samples and on a universal testing machine, set the same cameras up and actually correlate that. That was our verification. We actually did a test to failure, either on dog bone samples or round samples for steel. And we used the DIC live to track it, and then we compared the value of their virtual stress and strain with what we got from the calibrated equipment. So that's one way to do it. With concrete, They typically, for concrete, do core tests. They don't usually do tensile tests. So you can do a core test and see what the value is, but you could do a similar type of thing, do a core test and have the DIC running while you're doing the core test to compare. So in terms of what we discussed last week with the ballistic case study and the head injury, this is just sequential images showing as this basically dynamic impact. You have a bullet, it gets shot, you have a Kevlar helmet, and the energy has to be dissipated. So what percentage of the energy gets absorbed versus what gets passed through the helmet to the human brain inside. So there's 4 things to keep in mind, factors to consider. You can have skull fracture, and this publication is also on Stellar. So these are the 4 criteria they used in evaluating the system. If there was skull fracture with damage to the underlying tissue, and they use like the crash test dummies, or if you've ever seen the show Forged on Fire where they test the weaponry, they used basically mock-up dummies with artificial tissue in some of these tests, so they could actually shoot bullets into not living samples, right? You can have shear injury from the rapid rotation, cavitation by the acceleration, or fractures to other components. So this is what they define as the 4 types of head injury or trauma. So you had asked the question last week based on the size of the ballistics. Was it IEDs or was it not? In this case, they were using 9mm ballistic, but I'll show you in the following slide. So this is just how they back calculate the energy that gets absorbed. It's just the integral over the effective area of that helmet. So it takes into account the thickness of the helmet, in this case Kevlar, and as well they assume a uniform thickness for the human skull. And these are the images from that publication. So what you're seeing here is on the point of impact, this is actually, they can map this, and this is how they back calculate it with the software. On the point of impact, they can actually, because they are capturing, from what I saw, it was approximately 5,000 frames per second. That's the rate of data acquisition we're talking about for this dynamic test. So as the bullet hits the Kevlar helmet, it is capturing at 5,000 frames per second, and because there's that many data points, they can then back calculate it out. So what you're seeing is point of impact and then energy versus section length. This is what I wanted to post based on your question last week. They actually put somewhat like an Ashby chart with respect to different impacts. So for the helmet, it's at this location, and it's on a mass versus velocity X and Y. So you see if you had an impact by a car, there's a lot more mass. If you had an impact from smaller arms, it would be in this region here. So it's actually, there was some argument years ago over the use of aluminum bats in college baseball. And there was actually similar research done on if somebody hits a line drive, the pitcher would not, with certain aluminum bats, if somebody hit a line drive back at the pitcher would not have enough response time to get out of the way. And that led to some changes in the allowable bats they use in College World Series. Similar type of impact between getting hit in the head with a line drive in baseball and getting this helmet shot with a 9mm through Kevlar. So pretty interesting research. I thought it was interesting enough to follow up with you on it this week. And just to tie everything in, as we talked about, how you view the human body as a structural material. So now you can actually do tests where people have probes, and they can do functional MRI and see the different parts of the brain light up based on some of these tests. The neural networks, artificial intelligence is where it's going. I can provide the link on Stellar to the article I saw where stroke victims who didn't have the ability to speak can now use AI neural networks, and the computer can read the alphabet based on what they're thinking. They don't have to speak. It's pretty interesting. So I wanted to tie that stuff in from last week with the human skull and anatomy. What I wanted to discuss this week is what's known as tribology. The study of friction and wear is known as tribology. And it's of contacting surfaces that move relative to each other. So one of the things we'll show in some of Da Vinci's sketches was very simple methods that he used to evaluate mixed mode effects of friction and wear on sliding surfaces, and he used those insights into a lot of his designs. He said the action of friction is divided into parts of which one is simple and the others are compound. For Leonardo, he considered the simple action as just a sliding friction where there's nothing resisting the movement. We get into compound friction when we start thinking about these pulleys and these other lever systems where you have rolling motion and the normal forces aren't, it's not just a dead weight load when you actually have things moving relative to one another. So Da Vinci called them the simple case and the compound case. In the current science, they have other names. They're known, we have your static friction here and we have your kinetic friction. So before we get into the equations, one of the examples of where Da Vinci started using these was in what's known as a slope meter. And when I first saw the device, I wasn't sure what it was. I didn't know if it was like a piñata, because you'll see in the other picture, it's not really clear how it actually operates. But when I read into it, it made more sense. The slope meter is basically supposed to be used with some of his flying machines. And what it would be a poor man's level from the mid-1400s to tell you if you were level or if you were on an incline. You have a plumb line with a ball at the end, and it hangs inside this protected jar. So what we're seeing in these images are the weights and scales related to measuring these screw machines. So in addition to the slope meter, he tied these ideas of friction and wear into various screw machines and cannon designs that he used. So this is the slope meter here, and what it would be if he was in one of his flying machines, he claimed that he could use this to tell if he was on an incline or not. So at first I looked at it, I didn't know what this entire device was, but you have to realize back then they didn't have a level like you have in construction industry where you can put a level on something. So this was a way to watch an angle and determine based on the angle of incline if he would be going up at too aggressive an angle. In aerospace industry, they call it mission profile. So when the plane takes off, you have the climb, and then you get to a part of the mission profile where you're just in cruise. So I try to tie it back into aerospace industry with respect to your pressure cycles. You have your pressure cycle on the incline. As you're going up in altitude, the pressure's changed. And then once you get to a stable altitude, you're in the cruise area of the mission profile. And then coming back down for landing is another pressure cycle on the fuselage and those structural components. So this would have essentially been something to measure the angle at which an aerospace vessel would go up and come down. So in terms of friction and wear, he used geometry, and in particular, You're going to see in some of these images, he broke these blocks down into smaller subsets. So he liked to use triangular diagrams, and he used the triangular diagrams as a way for him to conceptualize proportionality. But when I was reading into it, one of the things is basically he was doing integration. He was just breaking things down into smaller geometrical pieces that would be areas under curves. So even though this is hundreds of years before Isaac Newton, he was in his mind conceptualizing the idea of integration in these friction and wear studies. What you're seeing here are just his sketches of one block moving relative to another. And his overarching thing that he recognized was a proportionality between friction, this coefficient of friction, and the weights of these blocks. So he did enough experiments that he could correlate a value of friction to the weight that he was placing on top. In terms of metallurgical terminology, so ASM handbook is for American Society of Metals. And there's quite a lot of failure analysis work where you have two different metals either wearing or up against each other. And in a lot of projects, I see people misuse the terminology. You have friction, you have wear, but there's actually subsets based on the hardness of the materials used, as well as if there's metal transfer from one material to the other. That actually, if metal transfers from one material to the other, it's called other things from a metallurgical standpoint. So I wanted to put a couple of the terminologies that I think are relevant for you guys in here. So wear is damage to a solid surface, the progressive loss of material based on relative motion. You have static friction, which is basically the simple case that Da Vinci identified. That is just when an object rests on a surface and there's a force that is opposing movement of it. You have the maximum force due to static friction. It's a function of relative surface roughness as well as the magnitude of the normal. So that's where your weight comes in. This image here is, this is already posted. This is from an article published in Where, and it has a good overview of the history of his studies on it. But what you're seeing in this image here was one of the first instances in which Da Vinci actually used that pyramid law and broke things down into triangles with respect to friction. What you're seeing here are his sketches on block experiments for the simple case as he identified it, and then the compound case when the blocks were not normal, not perpendicular to a flat surface, but when the blocks were on angles, this would be compound cases. Tied it into pulley systems and other levers that we had already talked about. And there's just more images from his notebook on his designs. So Da Vinci used the noun confregazione, means to rub together. So in that definition, you'd actually think you're talking about wear. So in Da Vinci's time, he was referring to friction, but he was interchanging the terms friction and wear. They have distinctive metallurgical definitions. So one of the things that is actually quite amazing based on the time when he did these experiments was his experiments, and you got to realize this was mostly wood on wood, that these were the materials of the time as we talked about, wood materials. He measured a coefficient of friction typically equal to 1/4. So as he changed the weight, he basically got data points and he was able to plot a 0.25 coefficient based on the weight versus the orientation of the wooden blocks. So the coefficient of static friction is mu s. All right, that is the measure of the roughness of the two surfaces. As we see over here, you have your static friction. It's less than or equal to the coefficient of static friction times the normal force. So if the normal force is at a 90 degree, if it's perpendicular, that's the simplest case. If it's in the compound case where those blocks are at an angle, you take the cosine of it. So it's that normal force acting down. And then you also have kinetic frictional force, F of k, which is equal to the mu sub k, which is the coefficient of kinetic friction, times the normal force. And the kinetic friction force is the force that opposes the object sliding across the surface. Some relative values of various materials. So the thing that I thought was pretty impressive was for wood on wood, the coefficient is 0.25 to 0.5. And in the 1500, Da Vinci was basically able to calculate that same thing just by geometry. Some other surfaces that are relevant. One of the things you'll often see is that the mu sub s is actually usually larger than mu sub k. All right, that's just a rule of thumb you'll see for most materials. For steel on steel, you have 0.74 versus 0.57. When you have aluminum on steel, comes into the metallurgy. When you have different materials rubbing up against one another, you get metal transfer in some cases when the frictional forces get high enough. They're called, some of the terms we'll discuss are called galling versus spalling. And these are metallurgical principles. So abrasion, how many of you have ever had to make a metallurgical sample and you grind and polish the sample, right? I know Gianluca has, but abrasion's the process of grinding or wearing away. One of the things is there is a hardness table that I'll show in the next slide. So the hardest material known to man is diamond. So on the scale, that gets a 10. Then you have alumina, gets a 9, and then goes down. So when you're deciding if you're trying to polish a sample, what material, you wouldn't use a material that's not as hard as the sample. So there's a hardness table I'll show you. But galling is where you have high spots, and essentially you can think of it as localized welding. It's how I was taught, it's metal transfer. So if you had one surface that was aluminum and one surface that was steel, the aluminum would actually be transferred onto the steel surface because of the friction. So you can think of it as welding because at such a scale, the metal moves from one to the other. You actually melt and ablate the aluminum onto the steel. With subsequent spalling and a further roughening of the rubbing surfaces, but that is not the same as spalling. And this is not spalling for concrete. This is spalling for metal, which is the cracking and flaking of particles. So this is relevant to the case study on rail that we're going to talk about. So if you ever take the T into campus, then if you ever look down, you can see spalling on some of the running surfaces. The hardness scale here, as I said, diamonds got the highest as a number 10. Corundum, that's basically alumina, that's at a 9. And then it goes down to talc with a nominal. These are actually, these materials are listed as essentially standards, that if you have other materials that are in between, you know talc is 1, gypsum's 2, all the way up. So these 10 materials have essentially been, these are what you would calibrate your hardness against if you know you have a certain alloy in between here. So a couple other types of experiments that Da Vinci did, all right? Rather than just moving blocks at different angles, he basically, if you think of it for rail, he did cartwheels and axles. He did experiments of friction on those types of things, which I look at as almost being, if you have rail and you have train cars, it's not that different than what Da Vinci was doing 500 years ago. He found that the more difficult rotational sliding cases, these would be related to bearings and gears. So if he was using metal rather than just wooden gears, he found that these experiments were more difficult because the normal force, it's a more complex calculation where he couldn't just get a graphing calculator and put the cosine of the angle in. So heavy rotors and half bearings are additional experiments that he used. One of the things that I thought was interesting about his personal style is, as you see, just out of the blue sometimes he just sketches people's faces in with his notes for experiments. If I went back to the earlier slide, this is essentially the same features of the face that you see where he did the block experiment in the earlier slide. So I thought this, when I saw this picture and then I saw the image with the friction, it's the same features on the face. He worked on a lot of different projects simultaneously, so he basically put information in multiple locations as a way to kind of keep all the things straight in his head that he was working on. And as I said, he had this mirrored method of writing where if you looked at it in a mirror, it would look normal, but he wrote things the opposite way. So that was just how his brain worked. So the case study for today is on rail. So in the US, you have what's known as FRA, Federal Railway Association, but the standards association that governs what the material requirements for that rail and ballast and substructure are. It's now known as AREMA, but it used to be known as AREA, the American Railway Engineering Association. One of the things that most people don't consider, unless they're trying to get somewhere and the train doesn't show up, is that broken rails and welds due to internal defects or anomalies, it is one of the leading causes of accidents in America. Not just commuter rail, you have to also take into account freight rail. So Conrail and all these other rail lines, sometimes you have commuter rail and freight rail that share the track. Sometimes you have dedicated track for freight. So if something's coming into a port and you have to get it to its final destination, you even up here on Mass Ave and Broadway, you see sometimes they used to have the circus come in once a year and they would bring the elephants and everything in. So I think of it in terms of when I see the rail. I worked on a project where rail fractured after the circus came to town, and it was something we had to take into account in the analysis. What you're seeing here, part of the rail profile, you have a rail head, you have a rail web, and then you have the base of the rail. What happens is these are based on numbers. So for typical commuter rail in the US, you'd see, if you looked at the rail on the side of the webbing, it will say 136 RE. So that is 136 yards per cubic foot. That's how they break down the weight of the rail. That 136 is a weight value, and then the RE just means regular rail. It'll often tell you also which manufacturing company made the rail and the year and the month of that bloom or ingot. So these are information that you see on the rail itself when you have to look at the rail and tie it back for a root cause inspection. Over time, what happens is, based on contact surfaces and the stresses, you wear away parts of this rail profile. So if you're on the rail, sometimes you'll feel the rail seems to drop sometimes, or this is areas where they usually have people on the train sometimes, and they have GPS locators, and when they feel that they're going over an area where there's wear, they make a note and they have their field crews go in and replace that. That's through, they're continuously welded rail sections, usually 20 to 30 feet sections. And if they have to go in and replace it, they will cut it out and do what's known as a thermite weld. So Professor Eager has talked about thermite welds with respect to conspiracy theories and 9/11. But that is how they actually weld the rail on site in most areas in the US. So the loads and stresses are very important. So one of the things that if you end up going into engineering and working for a company that deals with inspections is you don't just have the weight of the train cars on top of the railhead. You have to think of this rail. You also have ballast substructure. You know, when you're on the rail, you see the ballast, all the rocks, and you also see the wooden ties. Sometimes there's concrete ties. You have to think of that whole system as being connected, because what happens is the loads get transferred from the train car, which would be the wheels would be sitting on top of the rail, but it gets transferred down through the base of the rail. And if you have an area that's been washed out, this will actually bend and you'll get deflective forces and things like that. So the ballast and the substructure is as important to understanding the loads as the weight of the train cars on top. And that's something that most people, it's not immediately intuitive because they just say, well, yeah, I'm sitting on top of the rail surface. But oftentimes, if they don't go in and do proper maintenance, that ballast is there for water drainage. And if the ballast doesn't allow the water to drain, you'll get blockages feet below the ground. And that can lead to soft spots where the rail actually flexes. So FRA actually places maximum values on how much that rail can deflect vertically as a train car goes over it. And if it deflects more than that, they have to take out that piece of rail and put new rail in. Couple things to note is that these areas of double curvature are oftentimes where you'll start to get fatigue crack initiated. So every time a train, if you have a train car, say there's 6 to 10 cars, each one of those cars has multiple wheels on it. So you're getting maybe 50 to 100 cycles every time a train passes. If you consider each one of those wheels going over a section of rail as a single cycle. So you have to realize you can get up to millions of cycles relatively quickly when you're running train cars all day. And then to understand that the different orientations, you have the transverse orientation. Longitudinal is the orientation of the train cars on top of the rail. And then you have vertical. So this is just another image on contact stresses here. What you're seeing is depending on how that train wheel touches the rail, you can have high spots and low spots on the surface. So one of the terminologies in the industry is known as flat spots. And what happens is in the fall, if you're in New England and you have leaves fall on the tracks, sometimes you'll have the train cars going over, and if the conductor on the train car has to brake and you don't have an immediate contact, if you have leaves as an intermediary, it will actually leave like burn marks on the rail surface. So these are known as flat spots. So this is just an image to see that it's that contact surface. So you also have to consider the issues with these train wheels. If the company has modified the train wheels in some way, it will affect the rail. And there's a whole bunch of types of defects that you can get with rail. So I can post this. This image is from this literature article. This stuff will be on Stellar if you're interested in reading on it more. But you have different types. This is shelling. It's called, one of the terminologies is called shelling. And it's basically, if you have an inclusion in the rail, you will get progressive degradation from that inclusion. Another thing to point out is you have these vertical split head. So one of the things I wanted to show is it's also known as a forging burst. So this was a project I worked on, and this wasn't rail that commuter cars go over. This was actually rail that a crane was operating on doing dredging in the middle of a river. So one of the things here is, as you'll see, this is quite a significant internal void. It's known, it has multiple names. I'll call it a forging burst. But this is a product of the manufacturing process. So this was present not from service loading. This was present from the manufacturing of the rail. Now, if you look at the running surface here, it looks perfectly fine. You'd have to use an ultrasonic inspection technique to detect this once it's in service. So that ties into some of the later slides, but one of the things is take a look at this is a cross section. Just take a look. The running surface seems perfectly fine. The base of the rail seems perfectly fine. So if you didn't do, this should have been detected prior to leaving the manufacturing facility is the point. And once it goes into service, these are very difficult to detect. So you can get a feel for how heavy that rail is as well. It ties into, for commuter rail, they have what's known as a Sperry car. And that's actually a rail car that at night while people are sleeping, and at least for the MBTA, they shut down the rail for X amount of hours. If you're in New York, they take certain lines of the subway out of service so they can do Sperry car inspections. And it's basically a rail car that has ultrasonic probes, and it goes over the surface of the rail and does in situ ultrasonic inspections of sections of the rail overnight. So that tells them indications if they might see something that is subsurface. As I had said, a couple things that's important to consider is that the ballast end substructure, so that's the cross ties, that's the bolt holes and angle clips, all of these parts together, they all act as a system and can affect these loading conditions. So moisture, soft spots, and then issues where the ballast has blockages underground all affect the loading conditions at the surface level. So the last thing I wanted to show here is it's not exactly the same as a Sperry car, but this ties into automation. Now a lot of robotics is tying into inspections. And this is for what's known as a phased array ultrasonics system for welds. So what you're seeing here are the probes. So this is the robotic, sometimes they're known as crawlers, but it's basically an automated robotic system that goes over welded pipelines. They have two phased array probes here. What he's pointing out in the image is the wedge angle as well as the different geometries of the probes. So the geometry of that phased array probe will affect the ability to detect. So phased array probes have the ability to sweep the angle, so it's not just a perpendicular. You can actually get sectoral scans where if you just went over vertically, you would miss a defect like that forging burst. This is a calibration block that they're showing. So in this type of probe, they have somewhere between 32 and 64 individual, or it's a 32 or 64 array. Now they can do up to 128, 256. So that's, each one of those is an individual data point, and it's taking basically simultaneously up to 256 data points simultaneously. And you get what's known as a C-scan image that shows if there's any any inclusions or any defects within the structure. That is what he's demonstrating on this video here. So this is the crawler in operation. This is your weld right here, and it's actually magnetic. So I'm not going to show you the whole video, but you can actually see it as he goes to put the system onto the pipeline. It attaches because it's magnetic. So this is starting to get approved by American Welding Society and other agencies to use rather than having a person manually do the inspection. When they have these long pipelines, if they have something that's robotic and the weld's essentially the same way for long lengths, they can do the inspection quicker that way. But it's only quicker if the conditions for the inspection are programmed correctly. So you have to realize if he doesn't have the probes oriented where the weld is, all that data is useless. If the liftoff distance between the wedge and the pipeline changes, the data is going to be incorrect. It's not going to be an apples to apples throughout. So there's a lot of variables that you have to take into account if you want to try to automate an inspection system. So I've seen a lot of publications. I worked a lot on inspections and automating of things. You essentially have to cater the inspection equipment to the type of product. So whether it's an oil gas pipeline, whether it's a rail system, whether it's a nuclear containment wall, you have to cater the inspection to the part being tested. Otherwise, you can't just take something off the shelf and try to transfer a Sperry car to an oil and gas pipeline. This is something that it sounds obvious, but people try to do it all the time and they end up having problems with their data. So the other thing that they won't tell you, but it's interesting, is portability of the equipment. So they actually considered for this equipment quite a bit the fact that it would have to fit in something that has to go through the airport and basically is the weight of a luggage, so you don't have to pay huge luggage fees. All of that went into the engineering of this whole unit. So if you have a field inspector, he has to actually be able to take this from site to site. And that was one of the things that it's also not very intuitive, but when you actually do this as a living, the weight of this and the ability to transfer it from site to site is very important. Portability and rugged ability are the two terms that they use in industry a lot. So it has to be able to work out in harsh environments, whether you're minus 50 degrees in North Dakota or whether you're 120 degrees in Texas. There's a temperature variation. There's also environment variation, humidity in Alabama versus humidity in Boston. So these are all factors that affect which ultrasonic probe you'd use and which technique you'd use. But just to tie it in, so this is phased array ultrasonics. The reason you use this is rather than radiography where you'd have to basically close the area down, you can now use phased array and it can give you the same depth of penetration through thick samples without having to close an area down because of X-ray generation. So these are the trade-offs that happen in industrial applications every day. But I wanted to basically tie this in. It's not the same as a Sperry car, but the science behind it is the same. The science used from a Sperry car operating on rail is essentially the same as the science they use for inspecting. So that's all I had for today. See you guys next week.